Welcome back. We're in circular motion. Worksheet number 2, problem number 5. We got the Cajun Cliffhanger ride, which was at Great America, and they took it out and disassembled it and such. It was very sad. But other similar rides still exist today, and they're even in carnivals and such. Let me show you a different one, but it's the same idea here. This is a camera that's mounted on the ceiling or something like that, pointing down in. You see that they're standing on the floor there, and they're in some can here, and the can is rotating around this fixed point in the center, and the can's rotating faster and faster and faster. So you can kind of see here, and then check this out. The floor drops away. So that floor is just dropping away there. And now there's no seatbelts or anything like that. And you can kind of see because this one guy is rotating around there and even going upside down. And people are quote unquote plastered to the wall there. How does this work? What is going on here? Why aren't these people falling down? This ride doesn't negate gravity here. Gravity still must be pulling them down. So then why are they on the wall? Which is a very, very interesting question. Okay. So that's what we're doing here today. Can we explain that? Let's see if we can use maybe forces to be able to explain that. I don't know. Let's find out. So here you're going to stand with your back against the wall like we saw with everybody in this vertical cylinder here, or can. And as the cylinder turns faster and faster, the floor drops out beneath you. So you're not on the floor, just like you just saw there. The ride has some internal radius of 2.5 meters here. So let's go ahead and let's draw that. So that's going to be rotating around some point there. And from the exterior of the wall to the point that it's rotating around there, that radius is going to be 2.5 meters. Now we have the period of revolution. So it takes 2.0 seconds to go around one revolution. So that's good. Oh, and that's a U in there. I put an O in there. That's bad. And determine the minimum coefficient of friction. I guess there's friction here needed to keep the passenger from sliding down the wall when the floor is dropped away. Okay, so let's go. Let's look at this. So clearly we're going to do our free body diagram for this person here because it's asking about friction between the person and the wall there. And so as you're thinking about it, that you might be saying to yourself, well, I guess maybe there is friction. I mean, they're pressed against some surface there, so maybe that's maybe reasonable that there's friction there. Let's think about this. Clearly, they got gravity pulling them down. Okay, that's a clear one. Now, do they have something holding them upwards? Well, they're not accelerating downwards, so then I guess so. And you're thinking of this, you're thinking to yourself, well, if I drop a coordinate plane here, let's drop a coordinate plane on here and go, okay, well, this is the radial dimension. It's pointing inwards there, so it's a positive radial dimension. That'll be the negative radial dimension. And then this one going up and down, that's not the tangential dimension because they're going in and out of the page right now. This would be like the y dimension there. And so you're thinking about that going, hey, what's going on with the acceleration in the y dimension? You go, oh, well, I'm expecting their acceleration in the y dimension to be 0, assuming that they're not moving around like that one guy was rotating himself and such. They're plastered against the wall there. They're not sliding up the wall, nor are they falling down the wall. So then something must be holding them upwards there. Even if you're not sure what it is at this point, something must. And if the acceleration is 0 in the vertical dimension, let's go ahead and let's just sum up the forces there. We're not done with the free body diagram yet, but sometimes this helps me figure out the free body diagram. Because here, I know that I have the force of gravity pulling us down, so that's negative. I must have something pushing it upwards there because I recognize that the right-hand side, this acceleration is 0, so then I get 0 on the right-hand side, meaning that I must have 0 on the left-hand side, or another way to say that is whatever force I have in that box there must be equal to my force of gravity. And so now I gotta, so I know that a force has to be there, and that force has to be balanced with the thing going down. Otherwise, you'd be sliding down. Why isn't it sliding down? Okay, well, then forces must be balanced. What force is pushing it upwards? Is it a normal force? Yeah, frequently we've done that, and it's been a normal force. But that would be like if they're standing on the floor there, but the floor dropped away. So they're not standing on the floor, so that can't be the normal force. So maybe we need to go back and let's run through all of the forces that are acting on this person here. So I have my 4 ranged forces. and I have my 3 contact forces there. Right? And so I just go through, anytime that I'm not sure, I just go through these. So I go, hey, what are my forces here? I have ranged forces and I have contact forces. So I'm just kind of doing this in brief notation here. What ranged forces do I have? I got gravity. Boom, I got that. I have the electromagnetic force. I don't have any charges that I'm talking about here or anything like that. I have the nuclear weak and the nuclear strong force here. So, nuclear weak and nuclear strong, that exists, but it's interior of my system here, so I don't have to worry about it. Electromagnetic force, again, there's nothing with charges that's holding us up here or something like that. And gravitational force, boom, well, we do have that, clearly. We already listed it there. Maybe it's a contact force. That would make sense. What contact forces we have? In no particular order, we have a normal force, we have frictional force, and we have a tension force. Okay, cool. Well, let's start with the ones that are easy. I don't have any ropes or anything acting on this person here, so I don't have any tension there. So then apparently this force has to be a normal force or a frictional force. Let's think. They are pressed against the exterior wall here. Well, that's one surface pressed into another one. And wait, hold on. One surface pressed into another, that sounds like a normal force, the definition of a normal force. And these two surfaces, they're back in the wall there, normal to them. Remember, normal means perpendicular. Normal to them is pointing this direction, the radial direction. That means that there must be some force that's pointing that direction there in the radial dimension there. And that would be a normal force. That's the definition of a normal force. They're back against the wall. The wall pushes their back, in this case, to the right, which is radially inwards. Okay, cool. So there's a normal force. Boom, boom. I got that. Great. And now when I have two surfaces pressed into one another, I always have the option of having friction there. So I think about that and I go, yeah, two surfaces there. I do have my back there. It could be rubbing against the wall. That could be kinetic friction, but it doesn't have to be actively sliding against the wall to have friction. I could have static friction too. And here we're looking for when the acceleration is actually zero, they're not sliding up or down, just like we saw there. So they're at a constant velocity in the vertical dimension, which is zero. Again, the acceleration is zero. So they're not moving up or down. So then this force that's pointed upwards here, that sounds like that's going to be static friction. Now, straight away, you might label that as the coefficient of static friction times the normal force. And yeah, that kind of saves you a step if you do it like that. So that means that down here, that this thing that's holding them upwards is the static friction there. And so then static friction, so the coefficient of static friction times the normal force is the same thing as my force of gravity. It has to be the same size so that they're not falling down or falling upwards there, you may say. The acceleration is zero in the vertical dimension, and their velocity is also zero in the vertical dimension there. Okay. Cool. So, okay, great. Now, what are we trying to solve for? Oh, remember, we're trying to solve for the coefficient of friction here. So I'm trying to solve for the static coefficient of friction here. So I look down here and I go, well, maybe I should just solve for the static coefficient of friction straight away here. Let's go do that. That might be helpful. mg divided by my normal force there. Okay. So, yeah, maybe. Can I put things in right away? Do I know m? Does it tell me? No, it doesn't. Interesting. I know G. Do I know the normal force? No, not yet, anyways. Maybe I can figure that out some other way. So I kind of got stuck here. That's okay. Let's go and let's sum up the forces in a different dimension. Maybe we'll get unstuck. I'm going to go and I'm going to look it up in the radial dimension there. And because I see that I do have a force going in the radial dimension, which makes sense because I'm expecting this thing to be accelerating in the radial dimension. Actually, it'll have some acceleration in the radial dimension pointed that way because I have an unbalanced force in the radial dimension there. Cool. So I sum up the forces in the radial dimension. And I go, what forces do I have? I have the normal force. Is it positive or negative? It's pointed radially inwards there, which we label as the positive dimension. And that's equal to m times a, and now all the same tricks that we've done before. I recognize that that acceleration is centripetal, and so that means that my acceleration is the tangential velocity squared divided by the radius there. So I can go and plug that in there, so let's go do that. I have the normal force is equal to mvt squared divided by the radius there. So now I think about that and I go, do I know these values? Do I know the speed? Well, it doesn't tell me that. Do I know the radius? Yeah, it told me that directly. Now, it didn't tell me the velocity here. That's interesting. But it did tell me something about its motion here. It said, hey, 1 revolution takes 2 seconds there. That's the period. Okay, well, that might be helpful because I think about that and I go, he's going around, this person is going around in a circle there. And I know that my tangential velocity is just, it's the same idea in this case as speed here, since they're not changing their direction in the tangential axis. And so that's just how far you're going divided by the time that it takes to do that. Well, how far does it go? Well, we know the radius there, so I know how far it goes, and the time that it takes to do that is just 2 seconds there. So I can go and I can take that and I can plug that in for my velocity there. So let's go do that. Maybe that'll be helpful. Now, careful, I got to square that. So I square all of that stuff. So I get 4 pi squared. Don't forget to square that pi. R squared over, don't forget to square everything, including that denominator there. And we go and clean this up. Let's go clean that up. The t squared goes in the denominator there, as you've done many times there. We'll put the constants out front. 4 pi squared r squared m divided by rt squared. And then you say, oh, one of those r's cancels out. We've done that so many times there. Should I have skipped that step? Probably. But I'll go and rewrite it anyways, just in case anybody still isn't there yet. And that's okay if you're not there yet. And so my normal force is equal to that there. Okay, could I go and solve for the normal force straight away? No, I don't think I can. I know 4, I know pi, I know r. I don't know m, I do know t. But so I don't know m, so I still can't solve for that. So I get stuck there, but I was stuck over here, but now I have 2 equations. Maybe I can get unstuck. What if I take this normal force and I plug it in for there? Let's see what would happen there. Maybe you see it already. So I go, hey, I have the coefficient of static friction. Let me see if I can draw that a little bit better. That's a little bit better. And that's equal to mg on the numerator there. And then this big mess in there, 4 pi squared rm divided by t squared. Now I'm dividing by this fraction here. Well, dividing by anything is the same thing as multiplying by the reciprocal. So I'm going to multiply by the reciprocal. T squared goes on top. So now I have mgt squared divided by 4 pi squared rm. And now I look at that and I go, wait, hold on, that helps out. Because m and m, I see I can cancel those out there. They divide by each other. So the mass doesn't matter of this person. Oh, really? The mass cancels out, and that means that the mass does not matter for the friction being able to hold them upwards. That should make some sense, because if I go back to this, I can clearly see that everybody they're different people, they have different masses, yet all of them are stuck to the wall equally as much there. Maybe not that one guy, because he's rotating around there. Clearly he is. Yes, he's stuck just as much there, because it is independent of the mass there, which is really nice for constructing a ride here, because you can put anybody on that ride, little kids, really, really big people, and it'll work out equally well for all of them. It's very interesting. If we didn't do that with variables, I don't think you would see that, which is why we should do that with variables. So now let's go through. Do we know all these others? I know g, it told me t. I know 4 and pi, it told me the r there. So now I can just put things in and solve there. G is 9.8. My t was 2 seconds, I believe. Yes, it is. So that's 4 then, because I square it. And then a 4 pi squared to let the calculator take care of the pi there. And then the radius was 2.5, if I recall correctly here. Yes, it is. And so now let's go ahead and let's put that in the calculator. Let's see what we get here. Clear the last problem. I got 9.8 times 4 divided by everything that's in the denominator. I want to keep everything that's in the denominator together there. So I'm going to do 4 pi, and do parentheses there, 4 pi squared times 2.5. Now I do need parentheses in this case because, again, multiplication and division have the exact same order. So if I didn't put parentheses, it'd all be tied for order, and then the tiebreaker is left to right. So it would multiply these, then divide by the 4, then multiply by pi squared, multiply by 2.5. And so the pi squared and 2.5 would be in the numerator if I didn't keep this in parentheses there. So make sure that you use parentheses where needed. Your calculator will always follow the order of operations. I've never found it to break that rule, but I sometimes don't follow the order of operations, and sometimes you don't follow the order of operations. So just keep that in mind. 0.397, 0.397. So I think about that and I go, hey, is that a reasonable value? Coefficients of friction are generally between 0 and 1. That falls in that range there. So it's probably going to be okay there. And it is. That's it. Let's reread the problem, make sure we didn't miss anything there. Determine the minimum coefficient of friction needed to keep passengers from sliding down the wall. That's it. Yeah, if it was higher than this, clearly there'd be more available friction to them. Remember that this static friction that we're calculating there, that is not the absolute value, that is the maximum value for that. So just if the coefficient of friction was bigger, if it was a grippier surface, so they made it out of rubber or something like that, that's a very high coefficient of friction between that and your clothes on your back or something, then it doesn't mean that this force upwards would be bigger than the force of gravity, and then you'd be accelerating upwards. No, remember that this is the maximum amount that static friction can be, and it'll be in friction will be anything between 0 and that max amount, but only up to that max amount as needed. And so depending on how hard you're getting pulled down in this case here. So that's it. That's how they're able to stick up there. Notice that it is dependent on how fast this ride is rotating there, and that's why you have the ground you're standing on the ground at the beginning for a specific reason. If you were going slower, if you rotate this ride slower, the T would be larger. It would take longer to go around. If it would take longer to go around, that would, the bigger number in the denominator there, that would make this smaller. That would make your velocity smaller. And then your acceleration would be smaller. And then your normal force would be smaller. And if your normal force was smaller, your friction would be smaller. And so then maybe at some point, the friction, if you're going slow enough, the friction wouldn't be as big as the force of gravity. It would be smaller than the force of gravity, and you'd be sliding down there. So it's dependent on how fast you're rotating this ride here. And so, it's dependent on how long it takes to go around. Now, if you ever ask, hey, why did you guys write it so that it gave us the period? Why didn't you just tell us the velocity? Well, think about it. If you were to watch this ride and I said, hey, go ahead and figure out how fast they're going, how are you going to do that? You'd have to get some fancy equipment like a radar gun or something like that. And even then it would be pretty hard, but it would be very simple for you to just measure how long it takes to go around there. It's very, very easy to do that and quite accurate too as well. And so that's generally why you're usually given some period here, because if you were to actually go do this, that's what you would most likely record there. And it's a pretty easy calculation. So anyways, that's it. Have a beautiful day. I will see you later. Bye.